Hello, my friends. Today I want to do some I want to do a couple of on this video, I should say. I want to do a couple of the homework problems, a couple of the exercises in section 1.8. I think we'll do two of them. Let's see. Here we go. So let me just share my screen. I'm gonna unstop my video because it takes up a lot of bandwidth, and then I'm going to share my screen. And here we go. So problem number 2 and problem number 6 right now. So let's go to so number 2, show that the sum of the divisors of the following integers is twice the integer itself. 6, 28, 497. I'm not going to do all of them. I'm going to do a few and just give you the idea. So we're over here. Now, first of all, the symbol for sum of the integers is this, again, it's a Greek letter sigma. So sigma, so let me just write that explicitly. Sigma of n sigma of n equals the sum of the divisors of n. That's just a symbol. And what are the divisors of 6? 1 is a divisor, 2, 3, and 6. These numbers all go into 6. 1 plus 2 plus 3 plus 6 is equal to 12. And for you math geniuses out there, 12 is equal to 2 times 6. But I'll just write that explicitly. In case you didn't pick up my point. 2 times 6. And for 28, well, the divisors of 28 are 1, 2, 4, and 7, and 14, and 28. If you add that all up, 1 plus 2 plus 4 plus 7 plus 4 plus 28, that equals 56, which also for you math geniuses out there is equal to 2 times 28. 2 times 28. And sigma of 496 being the sum of the divisors of 496. Well, the divisors of 496, now 496, by the way, is 16 times 31. That helps a lot. So the divisors are 1, 2, 4, 8, 16, 31, 62, 124, 248, and 496. If you add all these guys up, you get 992. And guess what? 992 is equal to 2 times 496. 2 times 496. 496. And that's what I said. Now, because there's much more involved in this, and you know, there's all kinds of stuff about this. These numbers, by the way, these are numbers, by the way. Let me just say this. So sigma of n equals 2n in the following cases. But when that happens, when sigma of n equals 2n, we call it a perfect number. When sigma of n equals 2n, we say n is a perfect number. It's just a, thing. And there's a whole history of perfect numbers, and goes back to the Greeks. They studied this. I found it fascinating. And you can prove a whole bunch of stuff about perfect numbers, which this problem is just taking things a little casually, just kind of looking for a couple of examples of perfect numbers. Anyways, let's continue on to the next problem, number 6. Okay, the problem number 6, show that there exists no integers x and y, 0 excluded, such that y squared equals 2x squared. Hence, show that there does not exist a rational fraction whose square is 2. Well, let's assume that there is such. Let's assume that there are 2 integers x and y, where y squared is equal to 2x squared. Now I'm just gonna assume here that x and y are positive. I can do that without loss of generality. So it's just but I need to do that because you'll see why I'm going to need to do that. So we're only restricting ourselves to and in general, this whole course, we really restrict ourselves to positive. We're going to, for the most part, really, at least the number theory part of this course, we restrict ourselves to positive integers. So it's all positive. So let's keep it all positive. Anyways, since y is equal to twice a number, y must be even because y squared equals equal to 2x squared. I should have said if y squared is even, then y must be even. That's really what I really want to say. So if y squared is even, y has to be even. There's no two ways about that. If y squared is even, then y must be even. I should have written that explicitly. I'm doing it right now. So y squared is even, then y must be even. And since y is even, it's twice a number. Yeah, I wrote this in a very clumsy, awkward way, but let's just go on with the proof. So let's just say, let's let y equal 2 times j. J is some integer. So this gives me y squared. So instead of saying y squared equals 2x squared, that means 2j squared equals 2x squared. And I expand that out, I get 4j squared equals 2x squared. And now I cancel, I reduce, and I get 2x, divide both sides by 2, and I get j squared equals x squared. But now x is twice the number because x squared is even, so x must be even. So let's let x equal 2k. Well, I'm going to do the same thing. 2j squared, which is what I left off up here, 2j squared now is equal to, which equals x squared, but x is 2k, so 2j squared is equal to parentheses 2k squared. Expand the parentheses out and divide both sides by 2, and I get j squared equals 2k squared. Well, guess what? That means that j is going to be even for the same reason, and let j equal 2r. And I do the same process, blah, 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 and I get 2r squared equals k squared. Now k has to be even. Now I can, and let k equal 2, whatever. This is going on forever. Basically, this process could just go on and on and on ad infinitum. But that's a contradiction because the x, y, j, k, r, they're all positive integers. They're all getting smaller. I mean, obviously, j and k are less than x and y, and r is going to be less than, j. These numbers are infinitely descending. And that's not possible with positive integers. It's one thing if they're real numbers. Real numbers can, or positive, even real positive real numbers that can diminish. Those can get smaller and smaller ad infinitum and still still stay positive, but not integers. They can't do that. So basically, it's a contradiction, which means our original assumption was incorrect. Our original assumption that there were two numbers x and y, where y squared equal 2x squared, must have been a false, and there are no such numbers, and that is the story. Let me just type that in. Type that in. Hence our original assumption must be false. And there are no such x comma y. I'm going to write here. I'm going to write here something called QED. You may have seen that. QED. QED is often written at the end of a proof. It's like Latin. It means quand. I forget, quand ergo demonstratum or something like that. It just means thus it is shown. It's typically written at the end of a proof. It's a kind of classic thing. Anyway, so this is a couple of the exercises. Just wanted to show you a couple of stuff, and that is it for this video, and we'll see you guys next time. Bye, everybody. It's been a lot of fun.